But what is your? How do we look into your YouTube?
It's going to be under my name or my Excel Center email address. If you go onto YouTube and search for Jalley, I think there's only one of me out there. Hopefully.
Okay. Okay.
I have a personal site also, but it's got all kinds of auto racing stuff on it. It won't have any geometry on it. So that's not the one that you want. I mean, you're welcome to come look at my auto racing stuff too if you want to, but won't help you with geometry. So as you guys know, this geometry stuff is all based on what's in OdysseyWare. If you've looked at OdysseyWare in general, what we have here are 7 lessons, 7 units. So that's basically, in order to stay on pace here, you pretty much have to try to get one of these units done per week. We are going to have a final that's not part of OdysseyWare. It probably won't be more than about 10 questions. I have not created that yet because they just told us recently that we had to come up with one.
Be nice to us, Jay.
I will, because well, I have other opinion about that final exam that I'll share privately if you want, but not right now. Needless to say, it is something that we got to do. They want us to have everybody throughout all the Excel centers have finals for each class. So we're going to do that the last week. So up till then, though, it's pretty much 1 unit a week. So if you're in geometry now, so you should know how to do graphing, right? Ordered pairs, points in a plane, all that stuff should be old hat. Yeah, maybe.
Maybe.
I know.
Oh yeah, see. I wondered about that. That's okay. I'll show you somebody that you probably remember. This our famous French friend. Rene Descartes and his infamous Cartesian graph, right? Frenchman came up with this. He actually started with this in geometry.
You guys go watch TV.
Go ahead and mute yourself, please.
Go.
Pri,
Hello.
put yourself on mute if you got others in the room.
Hold on.
Okay. So a lot of the beginning of this stuff from graphing actually came from geometry. So you probably are familiar with this graph from your time in algebra, the 4 quadrants of the coordinate plane. Every point that you place on a graph like this has an X value and a Y value. The very center of these graphs is 0, 0. This is like a traditional horizontal number line. That's the x-axis. The y-axis is like a thermometer, a vertical number line. So that part should not be any big surprise to anyone. Now, how it gets used is a lot like this first example here. If you've ever looked at paper maps, not getting the right one on the screen there. Sorry about that. Paper maps are based on a coordinate system. Okay, can everybody see the map of Illinois there?
Mm-hmm.
Yeah.
If you had a paper map, and I love my paper maps when I'm traveling, although I use Waze and Google Maps all the time, I still like a paper map occasionally to look at. you're going to have a set of letters or numbers across the top and letters or numbers along the side. And where those two come together, that's the coordinate of a location on a map. And these graphs are basically maps for points. So if you looked at this Illinois map, what city shown on the map is located closest to Chicago? Gary is, that's right.
Gary.
These two dots right here are the closest. Not a straight line like we're used to dealing with geometry or algebra. But if you follow these roads, you got to go a greater distance to get to Beloit, Wisconsin, which is a fine little community if you've ever been there. We used to play basketball against them when I was in college. Davenport, Iowa, I was just there last weekend. Blitzed right through it. Just outside of Davenport is the world's largest truck stop. If you're ever going west, you have to stop there. I'm just kidding. It's a bizarre place. It's like a shopping mall for truckers. So here's a little example of how you can come up with any kind of shape that you want if you place enough points on a graph. Here you've got a star shape based on about 10 points, it looks like, or maybe 12. Ordered pairs.
The coordinate axes are the two number lines which have 0 as the intersecting point. The horizontal line is the x-axis, and the vertical line is the y-axis. To put a point on the plane, you need to know two coordinates, the x-coordinate and the y-coordinate. These are written in parentheses as x, y, and this is called an ordered pair. In an ordered pair, the x indicates where the point is located on the x number line, and y indicates where the point is located on the y number line. So, in this ordered pair, 3, -2, the point is found where the invisible line from the 3 on the x number line meets the invisible line from -2 on the y number line. Put a point in this location to mark the coordinates. If the ordered pairs form a line, you will plot all of the coordinates and then connect the points with a straight line.
And that's what you're used to seeing in algebra. That would be something that could be reflected in a linear equation because it's a straight line. Every ordered pair like this is a single point, and it's two consecutive movements. This one up here in quadrant 1, everything is positive. To the right's positive, up is positive. And if you think about the way number lines work, that'll make sense. Because if you're at 0 and you go to the left on your number line, then you're in the negative numbers. You're below 0. On the y-axis, if you're at 0 and you go down, well, what happens with a thermometer that's gauging temperature when you go below 0? Those numbers are negative also. So it's two consecutive movements. We're going to go 3 to the right and 2 down in order to place this spot 3, -2 on the graph. That should be old hat for everybody. And so most of this first piece here is a reminder about what plotting involves. Here you've got a series of points that don't create lines necessarily. They're not always going to be in a line. This graphic right here is, I think, very helpful because if you look at the quadrants, 1 and 3 are opposites. Everything in this quadrant 1 is positive. Everything in quadrant 3 are negative because left and down are negative. 2 and 4 are also opposites, but they're backwards opposites. Negative positive versus positive negative. And if you notice, they're always in the format of x first, comma, y. I always thought that sometimes these look like owls or figures, like in quadrant 1 looks like somebody has got knocked out with the little X's in their eyes or the crosses. In quadrant 3, they're sleeping, you know. So if that helps you remember where these points will get plotted, then that's what you need to do. See, here's the kind of problem I think Pri was talking about here. If we're trying to plot these points here, we gotta take this point here. You see how I'm clicking and dragging? There's point A. It should stay there, but for some reason in the teacher view, it does not. If it doesn't work for you, then we need to talk. But that's the goal here. These are all drag and drop. There should be A, 1, 1. B should be -3, 0, right there. C, -4, oops, -4, -1 in this location. And for D, 3 over 2 down. So a lot of plotting practice in that first exercise. Any questions so far other than whether or not this thing works?
No.
Jay.
Yes.
So when we are dragging that little dot on the bottom.
Yes, because that's your point that you're trying to put on the graph.
Okay. Okay.
And then when you get to the right spot, you let go of the mouse button, release the mouse button, and it should stay where you dragged it.
Okay.
In theory, theoretically. So hopefully that will work. And if it doesn't, I don't know, sometimes sites work differently on a Mac than they do in a Windows environment. So you just never know. If it doesn't work with the iPad when you try that, then you probably will have to go to a different type of device.
Yep.
There is a bunch of theories.
You'll see a lot of that, yeah. Now they're towards the end here, they're doing the opposite. They're giving you these letters and asking you to identify which one of these ordered pairs over here correctly goes with the letter. So which one of these XY combinations is for letter F? F is over here. Going left 5, so that's
Three.
be -5.
Negative 3. 5, 0.
3.
It's 3, right. So all you're doing for this one is you're filling in the box with the correct and corresponding ordered pair number, and then checking at the end. It'll even, I don't know if you guys are able to see this or not, but if you have a show hide button, it can help you identify these things specifically. And you get all the way to the bottom. Here's that star example earlier. Which point has the coordinates of 2, 0? And you only got 3 choices on this one.
It's J.
I hear 2 different answers. Got to remember, X comes first. Left or right comes first, so it is J. Because we've gone 2 to the right, but 0 up or down. This is the opposite. This would be 0, 2.
Right.
A is 0, 2. X always comes first. Questions, anybody? Now this is going to seem a little bit strange, these next 3 sections. They talk about undefined terms. Points, lines, and planes. These are strictly theoretical. They have no dimensions. You can't, when we draw a point or a line or representation of a plane, That's all it is. It is a representation. To a mathematician, a point has no shape. It has no thickness. Neither does a line. A plane is one of these things that goes on like a flat sheet of paper that goes on forever in all directions. Well, how are you going to represent that in the physical world? Again, these are theoretical constructions, or like it describes here, abstract concepts. So we use pictures, representations of those things. Why didn't that come up for me? There we go. So here's the explanation. Not going to be able to see that maybe. You guys will probably have better luck looking at the video than I am right now. See, points, they have no shape, color, or physical properties. It's imaginary. A point is just a representation of some location. And it's not displaying correctly either. So here's what a point is all about. And you'll see similar explanations for the lines and planes here also. Well, that's not helping me either. There we go.
In geometry, some words such as point, line, and plane are undefined. In order to define these words, you need to use words that need further defining. So they are left as undefined words. However, it is important to have general descriptions of their meanings. You can think of a point as a location. A point has no size, mass, or volume. It is completely imaginary other than the location that it points to. A point is represented by a small dot and named by a capital letter. Let's consider the relationships between two or more points. Is it possible to draw more than one line through any 2 points? As illustrated in the graphic, the obvious answer is no. This leads to the term collinear. As it is always possible to draw a line through any 2 points, 2 points are always considered collinear. 3 or more points are considered collinear only if they lie on the same line. A group of points that lie on the same plane are coplanar. Any 2 or 3 points are always coplanar. 4 or more points may or may not be coplanar. The figure on the left shows coplanar points A, B, C, and D. And in the box, there are many sets of coplanar points. Points P, Q, X, and W, for example, are coplanar. The plane that contains them is the left side of the box. Each of the 6 faces of the box contains 4 coplanar points, but these are not the only groups of coplanar points. For example, points Q, X, S, and Z are coplanar even though the plane that contains them isn't shown. It slices the box in half diagonally.
Some new terms here that bear repeating. Let's see, where is it? Collinear. This is something that you would be expected to know and to be able to identify collinear points. 2 or 3 or more points on the same line are collinear. Coplanar is another one that is important to know, and these are good representations that you'll see a lot in geometry. And especially if you look at this box here, this box shape, when you see these dashed lines here, you know, they're trying to show this 3-dimensional thing, this rectangular prism or box. They're trying to show it on a 2-dimensional screen or a 2-dimensional board of some sort, whiteboard, blackboard. And in order to do that, they're representing the unseen parts by dashed lines, the part that's behind what you're looking at. and you'll get an idea about this yourself if you pick up a box of Kleenex or a shoe box and you hold it out in front of you and you look at the box kind of on an angle, you're going to see certain parts of that box, but there are other parts that you know are still there because the box is a box, but you can't see them. You can't see through the box. So you'll see a lot of this type of thing in geometry. There will be three-dimensional shapes that they're representing, and the parts that you can't see physically that are on, they're not on the front, they're behind or on the back surface that's hidden, are always going to be represented by these kind of dashed lines. The other thing that she said at the beginning that's important, geometry has lots of rules about how things are displayed or how they are written. Capital letters always signify points. Very important. Lowercase letters represent lines. So you have to remember if you're talking about points, we have to use capital letters to show those. Questions, anybody? I got out of that too soon. Okay. So most of the rest of that particular lesson is a recap of that. One video, some explanation of what points are. Okay, now the next one this isn't what I was wanting to see. Hang on just a minute. Somebody have a question? There we go. That's the screen I was looking for. So the next two sections here about lines and planes kind of basically follow that same pattern, explaining what it is to have a line that is an abstract concept.
Think of a line as a series of points arranged incredibly close to each other that extend in two opposite directions without end or curvature. You can name a line by any 2 points on that line. In symbol notation, any 2 points on the line are written with a small line over those 2 letters. This is read as line RS. Another way to name a line is with a single lowercase letter, such as T. 2 lines that lie on the same plane are called coplanar. As lines extend on forever, they must either be parallel or they must intersect. This is not true for non-coplanar lines. As you can see from the illustration, one line is an extension of a front face edge, and one line is an extension of an edge on the right face. These 2 lines are not parallel and will never intersect. These type of
What she's talking about there is if you took this edge of this box and you made that a line that extends on forever, and you took this one, the back edge here of this side, those 2 lines are never going to intersect. Those are not coplanar. They will never intersect, and they're not going to be parallel. But this line and this line, the top and the bottom edges of that front face, those are parallel. Same thing on the end, the top and the bottom line faces are going to be parallel. They're going to intersect with the other edges. When I mentioned before about how geometry loves to have things written out in a specific way, this is another good example. That lowercase t is another way to identify that line. And this double arrowhead over the letters RS, That is traditionally the way to show a line of some description that goes through identified letters, identified points that are on that line. So it's got to have the arrowhead at both ends of it, though, to be a line. Because there are other symbols that you'll find out that are very similar to that, that some have no arrowheads, some only have one. And those represent different things in geometry. Okay.
Intersect. These type of lines are called skew lines.
She said that awfully quickly. The word she's using is skew, S-K-E-W. Probably have never used that word before, but if it's used a lot in construction, if you have something that's askew, it's not lining up correctly. It's not oriented the way that it should be. So here's the similar example was what I was talking about. You've got one line in this plane going this direction, the other in a different plane going another direction. They're not in the same plane. They're not going the same direction. They will never intersect, and they're not parallel. So a lot of different terminology there already. Skew, coplanar, collinear. Now we're going to look at planes.
Think of a piece of paper that is magically enhanced to grow forever. This would fit the definition of a plane. A plane is a flat surface that has no thickness. A plane contains an infinite number of lines and extends without end in the directions of its lines. You can name a plane by either a single capital letter or by at least 3 of its non-collinear points. Those are points that wouldn't fall on the same line. These two planes are called plane P and plane ABC. All of the points A, B, and C are said to be coplanar as they all lie on the same plane. The same can be said for any lines drawn on a plane. For example, a line drawn through AB and another line drawn through AC would be coplanar. Let's look at a slightly more complex illustration and summarize what you have learned in the last 3 lessons. Can you name the 2 planes shown in this illustration? The green plane could be named by any 3 points from the group of points F, A, L, I, and C. For example, the green plane could be named plane F, A, I. The pink plane could be named plane G, O, B. Did you happen to notice that the 2 planes intersect? The intersection of 2 planes always occurs along a line. In this illustration, the intersection of the 2 planes occurs along the line X, Y. Would the lines IC and GB be coplanar? The line IC is on the green plane, and the line GB is on the pink plane. Therefore, they could not be coplanar, but would be known as skew lines. Recall that skew lines are lines that are not parallel and do not intersect. Are the lines EO and GB coplanar? As all 4 points are on the same plane and you can see the intersection, they are coplanar.
They did intersect.
Nathan thinks they did intersect.
Could be point plane, and you can see the same plane, and you can see the
IC and the GOB, the cross. Yeah, that one.
Yeah, they're on different angles though.
Huh?
See, this is part of the problem with geometry. You have to try to train your brain to think about these things in 3 dimensions, because that line IC is on this plane. It's going that direction, off of the edge of that plane. The other line is going this way on this plane. They're not crossing. It only looks that way because this is, again, you're trying to take something that is three-dimensional and you're trying to represent it in 3 dimensions.
Oh. There's that dotted line right there. Right?
But the dotted line is just the edge of that green plane. That's
Right,
the,
but if you like set it down and 3, you have it going the 2 different ways.
you got to think about things that are going like this.
Right. Okay.
So on this one, it's going off in that direction, and the one going through here, see this is like an intersection going that way, and the other one doesn't even cross it. It's above it or to the it's nearer to you than the other one is. If it were intersecting, it would be intersecting at a point because 2 lines will intersect at a point. And so they would have to have identified another point by a letter on there to show you that it's intersecting. It's another thing about geometry is you can't assume anything. You have to be able to physically see it, and it has to be identified in order for you to say that something is something. In other words, that if it looks like an intersection point, it has to have a letter identifying it as a point to show you that it is truly intersecting. Because they're not going to put an intersection on there and not identify it. That just doesn't follow the way geometry people do things. It's going to be shown, and you'll see that more when you start looking at proofs, because we can't assume anything. If things look like they're parallel, you have to identify some reason that you know that they're parallel. You can't just say, oh, they look like they are. It has to be proven by some representation in order to know for certain that they are. And this is one of those cases where it's not showing us that it has to be an intersection on a point or it's something else. Those are just 2 skew lines. But it's a good point. I'm glad you brought that up because you'll see that a lot in geometry. And that's part of the reason why some people have trouble with geometry, because you gotta train your brain to think about things, to look at them in a slightly different way than you might be used to, because it's 3-dimensional. And anytime you're trying to show 3-dimensional things in 2 dimensions, it can be tough. So all of that goes into the first quiz, which I'm not going to do, but I'm going to skip down here to the definitions. Those were undefined terms, those abstract concepts. Now you get into some defined terms. We're going to have to identify segments and rays. We already talked about collinear. We're going to have to be able to know how to identify and name examples of segments or rays, and figure out if 2 lines are collinear or not. Big list of definitions here. The ones I want to point out as for emphasis, this is one of them: bisector of a segment. Bisector is cutting something exactly in half. If you think about a bicycle, it's got 2 wheels. A bisector cuts something into 2 equal parts at its midpoint. So if I'm standing here in my classroom and I want to have a bisector of a line that runs between these 2 walls, that bisector is going to cut the room exactly into 2 equal pieces. The length of a segment is just the distance between the endpoints of a segment. Line segment, it can be a part of a line, but it's not a line. And that may sound crazy? But a segment is just a piece that's between two stopping points. A line goes on forever. It might go through some points, but it goes on forever. A segment stops at defined endpoints. That's a big difference between a line and a line segment. And you'll see that when we start looking at how these are spelled out or written up also. The midpoint of a segment is where it's divided into two equal segments. Then we have something called rays and opposite rays. These are like you might expect if you have a ray of sunlight. Well, where's that ray originate? It originates at the sun, and it goes off in one direction. So that's what a ray is too. And you'll see like if we're talking about writing up a segment AB, that's one of those descriptions that's going to have just a line with no arrowheads on it, a little short stick basically above the letters. A ray is going to have one arrowhead on it because it shows, it's a representation to show that it's starting at point A and it goes on infinitely in the direction of point B. Now, opposite rays create a line because now you have a common starting point but going in opposite directions. So now you have rays going off to infinity in both directions, and when you put them together, you have a line. A lot of these definitions are going to come back over and over and over again. So here's what I was talking about a minute ago with the how segments are described with the letters. Here, you've got a segment shown as segment AB. Well, beyond that, you have these arrowheads. So you know that this segment AB is part of line AB, but all we're worried about for this exercise is that piece that is actually between A and B, or if you write it the other way, between B and A. If you notice, over the top of the letters is just that little stick. There's no arrowheads on it. So that's how you know it's a line segment. You get down here below that and with these three examples under model 5, here's two segments that are not part of lines. Here's a segment that is part of another line, but all we're interested in is the segment between the letters. These are the endpoints. Now, the big difference between a line and a line segment is you can actually measure how long a line segment is. You cannot measure how long a line is because it goes on to infinity in both directions. So a lot of what we end up doing with measurement for line segments comes back to using things like the distance formula that you might remember from if you remember doing that in algebra, maybe not, but we're going to use the distance formula a lot to try to figure out how long a line segment is once you put it on a graph. Here under model 7, you have a representation of a point M. It's telling you that it is the midpoint of the segment AB. So since it's the midpoint, you've created two equal smaller segments. AM going to be equal to MB. And that's all because of the definition of midpoint. If you drew a line through that point M, you would have the bisector. So the idea of bisector and midpoint kind of go together. Get down here to model 9. Now we're talking about rays. This is a single pointed arrow, one arrowhead in your description. Ray, and it starts, the first letter is the starting point, the second letter is the other point that it goes through. AC, ray AC is this one. Ray RS starts here at R and goes through S that direction. Ray XY starts at X and goes through Y. Again, the arrowhead is the tip off that is a ray. It's not a segment. It's not a line. Model 10 gets into the opposite rays. A, B, and C. You've got BA going this direction, going off to the left, and BC going to the right. Those are opposite rays. BD is not. It's not collinear. D is on a different line. D is on a line or a ray with B, but not with A and C. Common endpoints going in opposite direction tell you if you have opposite rays or not. Good quick summary down here. This I would encourage you to get into your notes somewhere, especially these, the way these things are written. Here's line AB, here's segment AB. AB here represents the length. What is the length of that segment? Here's ray AB, here's ray BA. People writing in geometry terms are very specific about all that kind of stuff. Now, the other thing that you're going to see, and this question number 4 here is another good example of how the stuff that's three-dimensional, they try to represent it in 3 dimensions, and you have to visualize it. The question is, are A, B, and C, are they collinear? Here's A, and there's B, and there's C. Are they all on the same line? Well, no. A and C are on one line. A and B are on a line. If this is the edge of this pyramid, C and B are on this line, the other edge of this pyramid. They're not all collinear. They're not all 3 on the same line. Collinear means on the same line. Now, though, if you look at this same shape and ask if they're coplanar, the answer is going to be yes, because now this A, B, and C, those are the points that define that whole side of that pyramid. So that side could represent a plane. Those are going to be coplanar. Those 3 points are all on the same plane. You'll see this kind of question and these representations over and over and over again. Pyramid is a favorite shape that you'll see a lot. The last thing I want to go through today is this last piece here with geometric theorems. A theorem is one of these things that if you can think mathematically, we have postulates, we have theorems and processes, including deductive reasoning, all these different things we can do to arrive at a conclusion. A statement is just another way of talking about a conclusion.
Often you make conjectures and then set about to prove if your conjecture is true. You've probably heard someone say that it's hot enough outside to cook an egg. If you wanted to see if that statement was true, you could grab an egg and possibly a frying pan and take them outside. One of 2 things will happen. The egg will cook or the egg won't cook. If the egg does cook, you will have a little snack and you will have proven the original statement was true. In math, a statement that has been proven true is called a theorem. In algebra, one way to solve a system of 2 equations is to graph both equations. When you graph y equals 2x plus 4 and y equals negative x minus 2, notice that they intersect at a single point, -2, 0. This means that the solution to the system of equations is -2, 0. This also illustrates theorem 1, which states that if two lines intersect, then they intersect at exactly one point. The power of this theorem is beyond just the one example, but that it says that all lines that intersect will intersect at one point. Mathematical theorems are very important things that describe a large number of situations. Proving these theorems will be an important preoccupation of this course.
I want to point out two other things here that really are good for you to get into your notes. And that's what you're going to see in a lot of these little videos that they include. There's going to be specific things like this. If you see this kind of a heading, a theorem is a statement that can be proven true, you probably need to write that down because it's there for emphasis. Because if we're talking about theorems, it's important that you know what that term refers to so we can have that conversation. The other thing, I go too fast. Here we go. This particular theorem is very specific because it is one of those things that has been proven to be true. Not sure why they call it theorem 1-1, other than the fact that it's maybe the first one that's shown up in the course. But it's another good one to remember because it's one of those things that is easily proven. If two lines intersect, then they intersect at exactly one point. That is part of the definition of a point or the intersection of two lines. It's just being said in a different way. So you'll run into that a lot in geometry. There's theorems. We're going to have to try to prove that they're true. And a lot of times we're going to be using different mechanisms to do them: deductive reasoning, inductive reasoning, and so on. So this whole section here talks about a variety of other theorems. It's important to remember, make notes on these things when you see these theorems being identified. Because they will come back up again and again. So anybody have questions about anything from today? So I want to save the stuff about the distance formula and the midpoint formula for the next class on Thursday. So that's kind of a typical way class might go. Some days I'll have other things to add in, either other videos or other slideshows, other things like that. Anybody have any questions? Okay, I'm gonna go ahead and end the class.